Okay, welcome back to Real Analysis. We have been starting with a construction of the real numbers by starting with a construction of the rational numbers. And we're today actually going to construct the real numbers for the first time. So let me just remind you where we've been so far. Last time we discussed our construction of the rational numbers as pairs, ordered pairs of integers. Now, of course, you think of rational numbers as fractions, and fractions are, in fact, ordered pairs of integers, aren't they? Right? You have a number on top and a number on bottom. And the way that we thought about this was, okay, these ordered pairs satisfied some notion of equivalence. And it's just the usual notion of equivalence that you're used to, that you were taught in grade school for how to tell whether two fractions actually represent the same thing. What we've seen is that this is, in fact, an equivalence relation. We've seen that under this definition, we can actually construct an addition and a multiplication that's well defined. So it gives this collection of ordered pairs a structure, an arithmetic structure. Okay, and it has an order, which, if you recall, an order relation satisfies two properties. Do you remember what properties those are? Good. Trichotomy and transitivity. So trichotomy is basically whatever the relation is. If we say it's less than, if you take two elements, x is either, you have exactly one of the following things true. X is less than y, or y is less than x, or x equals y. Okay. And transitivity says that if x is less than y and y is less than z, then x is less than z. Okay, so that's an order relation. And Q, in fact, has a nice order relation, and we define that as well. But the message is, it's exactly what you learned in grade school. Okay, so from here on out, now that we've carefully constructed the rationals, we can think of rationals as fractions. Okay? And it contains the integers in a very natural way. Okay, we also saw that Q, in fact, is nice because not only does it have these arithmetic operations, but it has the ability to solve certain equations that we couldn't solve in the integers before, right? So for instance, 3x equals 5 can't be solved in integers for x. But it can be solved in the rationals because the rationals are a field, okay? And it satisfies certain addition properties, which, if you recall, we labeled by letter A, 1 through A5, and some multiplication properties, M1 through M5. And then a final property, which is the distributive property, which basically says that addition and multiplication have to play nice with each other. Okay? You should be able to multiply. You should just be able to distribute addition over multiplication over addition. Okay? Okay, and we saw that, in fact, the rationals, not only do they have an order, and are they a field, but they're an ordered field, which, in addition to those two things, means what? That the order and the field properties, operations, need to what? Play nice with each other, right? In particular, if I look at two rational numbers and I add the same thing to them, then their order relation should stay the same. Or if I multiply them by a positive number, rational number, then they should still preserve the same order. Okay? Okay, great. So this is what we talked about last time. And we finished by noting that the rationals are not large enough to solve all equations. Okay, so in particular, this equation might come up if you were looking at a right triangle, length 1, and you know by the Pythagorean theorem that the hypotenuse has a length that solves this equation, x squared equals 1 squared plus 1 squared. And yet, there's no solution to this equation in rationals. This is what we discovered last time. Okay? Okay, so what is our plan for today? Our plan is to begin to rectify that problem by looking for a construction that would allow us to solve equations like that, x squared equals 2. Okay, so here's the plan for today. I want to construct the real numbers. Okay. And in particular, I want to show you a construction due to Dedekind. These are called often called Dedekind cuts. In 1872. There are actually several ways to define the real numbers formally, but this is one that we'll use because it only involves the kinds of ideas we've discussed before. So what do I mean by construct the real numbers? Well, here's the idea you should have in your head. If I have a number line, because we have an order, we can place the rationals along this number line. So for instance, here are the integers, right? And then here are some rationals. Okay. A few of them, right? Not going to write them all, obviously. Okay. And, well, what do I have? I have here, maybe there's a number line. Here's some of the integers. The rationals are in orange. But there are some holes in some sense, right? If the Pythagorean length, square root of 2, what we're calling that the square root of 2, we actually haven't defined what we mean by square root, but if you look at the hypotenuse with side lengths 1 and 1, it's a length along this line, and yet there isn't a rational that spans that length, so this might be the hypotenuse. That's a hypotenuse length of this particular triangle. And yet, if we look for this particular length here, we have a problem. There is not an orange point right there, in some sense. Okay, so this thing has holes. So, what does it mean to construct the reals? Well, what I mean is, I want a construction that only depends on things I've already defined. Just like the rationals, how did we construct those? We define the rationals in terms of integers, okay, as ordered pairs of integers, but in a fashion that only depended on the things we defined before. So if I wanted to define the real numbers, I can't say let's fill this in because it doesn't even have any meaning. What does it mean to fill in this line? I don't even know where the holes are, right? So how will I get at the fact that I have some gaps here without talking about the gaps? Okay, do you see the problem here? That's the question. Okay, there are a few ways to do this, but that's the question. So, any ideas? How might I get at the fact that there's a gap here? Let's see. Well, here's one way to think about what's going on. If I look at all these rationals here, okay, so maybe x squared equals 2 does not have a solution, as we've seen in Q. Okay,